This video is a supplementary video to the paper titled Exo-Glove Shell, a hybrid rigid soft hand wearable robot for thumb opposition with an underactuated tendon-driven system. Exo-Glove Shell was developed with two main contributions. First, this research proposes a novel fabrication method that uses rigid metal outer and soft garment. The metal outers were used for the reliable actuation, while the soft garment was used for easy wearing. When the robot was fabricated with only the soft garment, a stability issue occurred when the robot is worn in a misaligned position. Previously, when the tendon biased from the middle with angle alpha, the tendon routing deformed in unwanted ways. This issue occurs even with small initial bias because the bias generates torsional torque that amplifies this bias. Here, even small initial bias is not negligible because the torsional torque amplifies as the tendon bias increases. We would refer this unwanted move of the router as tendon bias in this video. Increased tendon bias was not preferred because it reduced the tendon momentum and made awkward postures. For example, the left video shows a situation where the finger cannot extend due to a decreased tendon momentum. However, the metal routers in this research prevent the amplification of the tendon bias even there is initial tendon bias. Therefore, it was possible to improve the reliability of the extension motion as shown in the video. It is because the rigid router generates resistance force when the glove tilts against the finger. For the validation, we have measured the tendon bias of the routers by applying torsional torque to the glove. The results show that the metal router sufficiently prevents the tendon bias. The use of rigid router also reduces the difficulties of fabrication. Previously, it was difficult to sew 4 layers of fabric which has only 20 to 30 millimeter width. It is because all the 4 fabrics must be sewn in a well-aligned state. However, when we fabricate the proposed robot, we don't need to care much about the location of the router hanger, which is a component that locates between the glove fabric, because there is no tendon path at the hanger. The reduced of total fabric layers and the thickness of the fabric also alleviates the fabrication difficulties. In addition, the two-step fabrication, a method to attach metal routers after glove fabrication, reduces the fabrication difficulties and enables easy modification even after fabrication is complete. In addition, due to a modular design framework, we can design metal routers by considering the requirements of each finger joint characteristics. This research also introduces a novel tendon routing that uses minimum number of actuators. For more detail, the robot was designed to assist 3 primitive hand motions using 4 tendon-driven actuators. The design strategy used to reduce the number of actuators consists of following 3 steps. First, we decided the target motion that is important for the activities in daily lives. In this research, we decided to assist the opposition motion according to the biomechanics studies. As a step 2, we designed a tendon routing that can use less actuators. In this study, it was possible to use only 4 actuators by using the underactuated tendon routing. Validation was conducted in step 3 to show whether the use of 4 actuators is sufficient. Since we developed the robot that assists the opposition, a volume of the opposition workspace was used as a performance factor. In step 1, we decided to assist total 3 primitive motions to make opposition. These 3 motions consist of 2 directional thumb motions and flexion extension of the index middle fingers. In step 2, we first started to use 6 actuators because the tendon can only transmit tensile force. After that, we found a tendon routing that has same functions even using 4 actuators. Then, the remaining question is, why are 4 actuators sufficient? And how can we obtain the appropriate number of actuators? To explain detailed derivation of the appropriate number of actuators, we represented primitive motions as 3 rotation motions. It is because we focused more on creating motions in each direction rather than controlling each joint inside the finger. For more intuitive explanation, we further expressed these rotation joints as linear joints. This video will explain the derivation of appropriate number of actuators using this linearized schematic. Derivation of the required number of actuators starts from a relationship between the joint angle and the actuation input. This relationship can be represented as equation 1, similar to the previous researches. Then, to make 3 primitive motions independently, there should exist an actuation input delta U that can make desired joint angle delta Q. One important thing is that the control input should be positive because the tendon can only transmit tensile force. According to the previous research, this requirement can be satisfied when the length of transmission matrix is same as the dimension of the joint angle output and null space of transmission matrix has at least one positive basis. In the case of routing with 6 actuators, we can see that it satisfies these 2 requirements. Therefore, we can infer that the tendon routing with 6 actuators is sufficient for assisting our 3 primitive motions. When we imagine a tendon routing that has transmission matrix as TR4 that requires only 4 actuators, the tendon routing of given system can be expressed as left figure. In this case, we can also infer that this routing can control 3 primitive motions because the rank of TR4 is 3 and there exists a positive basis in null space of TR4 matrix. In other words, we can say that tendon routing with 4 actuators can also control all 3 primitive motions. However, when we think of any arbitrary transmission matrix that uses 3 actuators, TR3 cannot satisfy the requirements because it does not have null space. For more intuitive explanation, the video also shows some example of how the tendon routing with 4 actuators works. For example, the robot assists thumb extension in the following order. First, the motor 3 fully releases the tendon in order not to apply tension to the TFE joint. After that, by pulling motor 2, the thumb extension can be assisted. However, the actuation of M2 will also make thumb adduction because M2 pulls 2 joints simultaneously. Therefore, we controlled the motor 1 to hold the TABD joint to prevent the thumb adduction. A procedure to assist thumb flexion is similar to the thumb extension assistance. First, the motor 2 fully releases the tendon in order not to apply tension to the TFE joint. After that, by pulling motor 3, the robot assists the thumb flexion. However, the actuation of M3 will also make medial index extension similar to the previous case. Therefore, we controlled the motor 4 to hold the IMFV joint. With these examples, we can infer that the antagonistic actuation enables to use only 4 actuators for 3 primitive motions. Although the mathematical expression and the graphical examples show that the use of 4 actuators is sufficient, this analysis is not exactly true in our case. It is because joint stiffness matrix and the actuation Jacobian is not constant. Therefore, we conducted additional analysis to validate whether the use of 4 actuators is sufficient or not. For the validation, we simulated the robot with 6 actuators and the robot with 4 actuators. As a performance indicator, we used opposition workspace because the main robot function is assisting opposition motion. With this indicator, it was possible to figure out that the use of 4 actuators is sufficient. As a next step, we also tested whether the actual robot with 4 actuators can assist 3 primitive motions independently. With developed Exo-Glove shell, we also conducted an experiment whether the robot can assist various postures. In this experiment, we divided the grasp into pre-grasp stage, which prepares the grasp, and the actual grasp stage, which contact with the objects. This video shows how the robot assists grasp postures belonging to head opposition mode. Similarly, this video shows how the Exo-Glove shell creates postures belonging to palm and side opposition mode. After the experiment, we also had an interview with a SSCI person. For more information, please see YouTube video link at the left side. Lastly, we'd like to show that the robot can assist various postures reliably even with less actuators.